All right, welcome to Math 15, and this is called the Chapter P. This is called the preparatory chapter. So we're going to cover in this chapter, there's 6 sections in here, but we're going to cover the basic concept of algebra. That's kind of what we're doing. So we're just reviewing algebra, and my rule of thumb is if you are absolutely bored out of your mind with this chapter, that means you are in good shape, very good shape. For the most of you, I think what's going to happen is as you go through this, like, oh, that's right, I never knew that, or you're going to sort of pick up a few things you might have forgotten, or you may pick up a few things that you sort of haven't had clear in your mind. Hopefully you don't pick up any things that you've never been taught, but hopefully just sort of like a remembering of what you have learned so far. And so in this particular section, we're just going to deal with real numbers and their property. Just kind of a quick review of all the types of numbers we use, notation that we use it, the absolute value concept, the distance concept, and the order of operations. Again, very, very basic as we start off. So the numbers that we use, and I think this is review for most of you guys, something called the natural number, sometimes called the counting numbers. These are the set of numbers we use. So if we're talking about counting the number of classrooms at West Hills College, we'll probably use this. All right? And then along the way, we had to make a distinction with something called zero. Usually the story that I use here is if you were a hunting party and you were counting the numbers of buffaloes that you killed, and if Johnny went on the hunt but he didn't catch anything, you have to really put a 0 for him, as opposed to Michael, that got sick, that didn't even go for the hunt at all. So notice there should be a distinction between the two. One went on the hunt, got 0. One did not even go on the hunt at all. And so, kind of interestingly enough, as we look at archaeology and anthropology, we find out that the concept of 0 actually originated in 3 different continents almost roughly at the same time. It's just sort of a fun little thing in history about numbers. All right. And then we have something called the integers. And so it is the whole numbers, 0, all the positive numbers, but we also have the negative numbers. And this really came about in history when we talked about having currency or having money. So I don't know if you guys are familiar with something called debt. Anybody familiar with something called debt or negative on someone's account? Where these you had to account for, I have $4 or I owe somebody $4. And so in this case we had to develop a number system to sort of keep that and understand that and distinguish that from people. All right. And then we have the rational numbers. Rational numbers are really all the things that we can put into a quotient of A over B. Just a quick distinction here. If you say there's something called fractions and there's something called rational numbers. And so again, this is a freebie, I'm not even going to charge you for it. So what is the distinction between a fraction and these rational numbers? And the only distinction is fractions can only have an integer on top of an integer, like 4/7 or -2/3. Those are considered fractions. Rational numbers, you can have the 4/7, you can have the -2/3, and then you can also have variables in here as well, as we'll get talking as we get into algebra. Okay, so you can have with rational expressions, you can actually have a x over 3 as well. That's why the distinction there. So fractions can't have variables in it, rationals do. And the other type of number we have is the irrational numbers. As we look at a graphic of this here, real quick here, we'll talk more about this here, but rational numbers are things that can be written as a decimal that it will either stop or start repeating themselves. Something like this, let's say 0.5. 0.5 is a decimal that has stopped. It has stopped at 0.5. Well, any decimals that stops actually can be written as a fraction. In fact, we know this as 1/2, right? Like this, 0.25. So we know that one, that's an easy one, that is 1/4. How about this one? I think you guys may know this here. 0.3 repeating. So 0.333333333 forever. I think you guys know that one as 1/3, right? The distinction is made. What happens if it's 0.3 without a bar line on top? In that case, it's still a fraction. It's actually called 3/10. Cool. So notice if a rational number or if a decimal stops or repeats, it could always be written as a rational number or a fraction or a rational expression. All right, the irrational numbers are decimals that don't stop and don't repeat. And so we'll talk about those in just a bit, but let's talk the whole concept of rational numbers here. So, the rational numbers. And so notice one, 0.01, 001, 0001, 00001. So the question is, does this stop and does it repeat? It does neither. It doesn't repeat itself because we should have a 0, 1, 0, 1, 0, 1, 0, 1. That would be a repeating marker. There is a little pattern here, but technically it doesn't repeat itself. Okay, so with the square root of 3. The question is, in fact, you guys with the calculator here, go for it. Punch in a square root of 3 if you have a calculator with you. And anybody tell me, what in the world is the square root of 3? All right, I got 1.732050807 blah blah blah. So notice this number again, decimals don't stop, the decimals don't repeat. All right, and then how about the famous pi? In fact, let's talk about this here first. What is pi actually equal to? What is equal to pi? That's what we should talk about. Because I wrote a little symbol that was a little wrong right here. Square root of 3 is actually, we should say approximately. The way we say approximately, we have an equal sign that sort of wiggles, a wiggly sort of equal sign. So pi is equal to, I think I heard one person say it, it's called circumference over diameter. So if you take a circle like this, you take the circumference, which is the length all the way around the circle, measure that, and divide it by diameter. This is what pi is equal to, not 3.14. When I used to teach high school geometry, what we did to sort of experiment with this, I had all the students bring in something that was circular. So some people brought like the top of a soda bottle. So it was just the top. Someone actually brought in those metal garbage can lid. And so what I had them do, I had them measure the outside, and then I had to measure the diameter across. And then what we did is we just took C or divided by B, and no matter what circle they used, no matter how big the circle was, it always came out to an approximation, right? Here it is. Pi is approximately 3.14159265336 blah blah blah. So notice the decimal point never stops, never repeats itself, so therefore it's called a irrational number. So that means really it can't be turned into a fraction. That's kind of what the whole meaning here is. Can't be a fraction. All right, so that's the irrational numbers. Let's jump to all of this here now. So we have the natural numbers, and natural numbers are really a subset of the whole numbers because it includes extra 0. Whole numbers are really subset of the integers because the integers include the negatives in there. And the integers are really actually a subset of the irrational numbers because you can make any integer into a irrational number by putting in a 1, right? How do you make a -3 into a rational number? You put a little 1 underneath it. 0, you can put a little 1 underneath here. 3, I can't do it this way here, but any integer can be turned into a rational number. Okay, on the other side, notice the rational and irrational are mutually exclusive, which means if it's irrational, it can't be rational. If it's rational, it won't be irrational. So that's the other side. So these guys are called the real numbers. These are the numbers that we work with, and sometimes in different categories. So if you're counting the number of buildings at West Hills College, you're going to use this number. If you're trying to distinguish between a little something of zero, you're going to use this one. If you're talking about debt and money and currency, you're going to probably have to use this one. And then if you're talking about anything that dissolves a fraction, if you're measuring something with a stick, you're probably going to use this one. And if you're doing some complicated geometry or anything with a circle, you're going to have to use an irrational number to help with that. And so irrational numbers really came from the Greeks about 250 BC. That's when we discovered, hey, we really need a irrational number, and that's where it sort of flowed from. It flowed really from the whole concept of the square root of 2. All right, and then, kind of interesting, a little bit more history here. And about 500 years ago, we actually learned that we can't just use the real numbers to explain our world. We actually have to use something called the complex number system. And that was only 500 years ago. Isn't that kind of crazy? Only 500 years ago, we had to develop a whole new number system. And I think you guys know it. You guys are pre-calc students here. The complex number system includes this little thing called I. Remember that by definition, I is the square root of -1. All right, the reason why this is not included in the real number system and in the introduction of algebra is because we normally work with real numbers. The whole concept of I is really in very specific applications. It doesn't occur a lot. I'm thinking electrical engineering is where you have the I concept. Anything that has to do with electricity, sometimes you incorporate the I function. Otherwise than that, we normally don't use I. Normally it's really right here. It's using fractions or counting integers or the irrational numbers. So used not quite often. But let's go with the rational numbers. Let's go with those here. So if we say that rational numbers are either decimals that stop or repeat themselves, let's see how we can do this. Can we express this rational number as a decimal? So let's go that way here. And so how we do it, again, just a total review of pre-algebra and algebra. And let's go with it here. So normally what we have is we have the decimal go in, the denominator go on the outside of our divide symbol, the 3 goes on the inside, and the numerator goes inside, and then we normally put in some zeros here. So 8 doesn't go into 3, so there's a 0 there. Bring up the decimal. 8 goes into 30 3 times. 3 times 8 is 24. So I've got a 6 remaining. Bring down the 0. 8 goes into 60. 7 times makes 56. That becomes a 4, and then we need extra zeros here because I don't see a repeat yet. So we bring down the 0, and how about a 5? And we get ourselves no remainder whatsoever. Perfect. So therefore we say that 3/8 is exactly 0.375. And notice what I did is I converted a rational number into its equivalent decimal form. Okay, that's the one that stops. Let's take a look at the one that repeats itself. Can't give you the answer yet. So if we look at this one here, we go 11 goes into 5, a few zeros in the back here, but let's go for it here. So we go 11 goes into 5, I don't think so, so put a 0, bring up the decimal point. 11 goes into 50 4 times, because that will make 44. And we subtract, gets you 6 left over, bring down the 0. So now 11 goes into 60. That's going to be 5 times 5 times 11 is 55. We get a 5 remaining, and then we plug in another 0, drop it down, and then we notice, hey, hold on, there's a repeat here. That's going to be 4. That's going to be 44. And if I do that, I'll get a 6 as our remainder. Then we have back to 5. Oh boy. So there it is. Okay, so how do we do this here? We say that 5/11 is exactly 0.45 repeating. So there's a little bar line, meaning this thing's going to repeat itself. And again, we have a rational number that is being made into its equivalent decimal form. Okay, so that's one way. One way to go from fractions or rational expressions into decimals. Then let's go the other way. And what we'll normally do in this class is if you look at your book, practice problem number 1, look at let's see, if you look at example number 1, example number 1 looks like this, and it should be, this is example. It's converting decimal rationals to a quotient, and this is what it is here. And then right afterwards, if you look on the page where there's example number 1, right afterwards you should see practice problem number 1. But there's no work for it shown. So in this case, we're going to be doing a lot of these. And sometimes if I don't think, for the most part, if we do all the practice problems in the section, we've pretty much covered the whole section. Every once in a while, I don't think the practice problems really do justice to the concept in this section. So what I'll do is I'll introduce more problems, just like we did before. I gave you 2 extra problems there in the beginning, converting the 3/8 to a decimal and converting the 5/11 to a decimal. So I'll add in a few extra problems here and there. But again, for the most part, practice problems do a good job. All right, so now let's go the other way now. So practice problem number 1, let's convert a repeating decimal to an integer, a ratio of integers, so basically a rational expression. But let's go back to the example problem, because I think the example problem will be a little helpful here for us to sort of at least take a look at real quick here. So how do we do this? We have to somehow get rid of this repeating decimal here. And so what we do is we designate x to be 7.4545454545 ever. Okay. And so now what we do is we want to multiply so that we get rid of one iteration of the repeating. So notice it's the 4, 5 that repeat. There's 2 integers that repeat themselves. So what we want to do is we want to multiply this by 100, because that'll get rid of one set, or one repeating set of the decimal. If I do that, I get myself 100 here. So notice that what happens, that's what I get here. It's 100x is equal to now 45 point, again, 45 repeating. And then what we do is we bring this one down over here. And then what we do is we subtract the 2. In fact, let me just erase this here. And let me subtract the 2 here. So 100x subtract x would give you 99. 745 subtract 7 gives you 338. And then the repeating section, you know that since it's the exact same number, we just got rid of all this repeating decimal. That's exactly what we wanted. After that, divide by the multiplier to x, and then reduce it as you can. In this case, 9 goes into both of them, and eventually we get 82 over 11. Okay, so that's exactly what we're going to do in terms of the next one here. The next one is 2.132132. We want to convert this into a rational expression. All right, what should we do? Well, first of all, we've got to name this. So I'm going to say let x equal 2.132132 forever. All right, now I have to get rid of the iteration of the repeating. So in this case, there's 1, 2, 3. There's 3 digits that are repeating themselves. So this decimal has to go all the way over here to start the repeat of 132. So it looks like 10, 100, 1,000. I have to multiply this by 1,000. So if x is equal to this, 1,000x is equal to 2,132.132132 repeating. Okay, so let's go back over here. So we're going to subtract off the original x over here. And with that, we get ourselves 1,000x subtract x makes 999x. And then again, 2,132 subtract 2, which would give you only 2,130. Divide through by 999. And I want to say a 3, I think, can go into those. 3 can go into 999 for sure. Let's just check. Does 3 go into 2,130? 3 goes in 21 7 times. There's no remainder. So 3 goes into 3 once. Exactly. And then 3 goes into 0 0 times, so how about 710 over 333, because 3 goes into 999, 333 times, and then that actually is the lowest terms right there, because that does not reduce anymore. Okay, and then the book, again, this is where the book does here. It talked about practice problem number 1, converting a repeating decimal. I thought it would be best also just to put in what happens if the decimal stops. How do you convert a negative 2.35 as a ratio of two integers? So introducing an extra problem, not part of the practice problems here, because I don't think the practice problem did justice to this concept. All right, what do we do here? Still the same thing here. We're going to let x equals a negative 2.35. And this time, since the decimal stops, all we got to do is get rid of the decimal. So technically, I got to multiply by 10, 100. I want to get the decimal all the way to the end of the number. By doing so, I have to multiply both sides by 100. So now it becomes 100. X is equal to negative 235. And I got it. So let's divide by 100 on both sides. And then, yes, you do have to reduce this. It looks like 5s will go into both those numbers. So 5 goes into 235. Let's see, 4, that's 20. Subtract, that makes 3 left over. Bring down the 5, and how about a 7 to make the remainder of 0? So how about a negative 47 over 20, because 5 goes into 120 times. Again, that is going to be in lowest terms as well. Okay, next is the number line. And again, what we do is we use the number line, and normally what we do is we put integers on the number line, right? We start off with 0, go to 1, 2, and so on. I think you guys know the number line. I'm not going to cover too much stuff here. And you will be required to place a few things on the number line. But once we get the number line, then we notice that 1 actually would be bigger than 0, and 2 is actually bigger than 1, and 3 is bigger than 2, and 2 is actually bigger than square root of 2. So we have something called order. There's order to the number lines, and the way we write the order is in terms of inequality. So if we say A is less than B, we have a little notation for it. We say A and this little weird funny symbol, and B. Okay? And so we have this whole concept of inequalities, but inequalities are really just the position of the numbers on the number line. We think about them real quick here in our brain, but really it's just the position of them on the number line. Okay, and then we have two properties. Not going to go into it. I think you should see this in algebra here. For any kind of number that exists, or any two numbers that exist, there's two properties here that you will need to know for calculus. I'm going to just look at them just real quick here. We could say for any number in the world there's something called the trichotomy principle. So how can we compare two numbers to each other? Well, either one number is smaller than the other, either the two numbers are exactly the same, or it could be that the first number is greater than the other number. So there's three different possibilities for any kind of number that you have on the number line. There it is. Okay, and then we have something called the transitive property. Again, something that you will have to use in calculus, and I'll give you a little name, something called the squeeze theorem. The squeeze theorem in calculus uses this concept right here. So if A is less than B, and we know for sure that B is less than C, therefore the transitive property says A then has to be less than C. Again, you're going to use this principle to get the definition of something called a derivative later on in calculus. But just want you guys to know, very important properties, important in calculus as you go through calc. Okay, but with it, let's go real quickly here through a few things here. Don't even need to write this down, just kind of real quick here. Just tell me true and false. Think about it yourself. We'll look at it real quick here. We're going to keep on going. All right, for the first one, negative 2 is less than 0. That is true. Good. 5 is less than or equal to 7. True. How about negative 4 is greater than negative 1? False. Okay, cool. All right, so we got that. Okay, and then the whole concept is how do we write out numbers? Sometimes we have something called sets that we have to write out. And there's two different ways to write it out. Something called the roster method. In the roster method, you just start listing all the elements you need. The other one's something called the set builder method. That's the one that we're going to prefer because sometimes you don't want to write all the numbers. Sometimes you can't write all the numbers. So the distinction really is right here. Set builder, let's do roster method first. Roster method first says, there, I got 1, 2, 3, 4, and 5. There it is. There's the roster method. I've just listed each of the elements. All right. Or we can write them as something called set builder notation. Set builder notation gives you a rule. And so we say, there it is, we put in these something called braces. This X means this is the variable in question, like this question. And then we have this little big bar comes across. This bar really means such that, or we say based upon the condition of. So again, the short way to say such that, so X such that X is a natural number less than 6, or X based upon the condition of, and then you write whatever condition you want inside here. So, and there's something called the set builder notation. We will use both. And then we have interval notation, which we'll also use here. So all the different ways we do this. Okay. A few more things here, I guess. We should say the empty set, if there's no answer whatsoever. There is no answer to this problem here. We have the little special symbol called no solution, or null set, with a 0 with a slash through it. Okay. Generally, what we do is we do use the set builder notation, and we should mention this right here. Sometimes we can't actually list all the elements. It's impossible. How about listing all the fractions between 0 and 1? So can you list for me, out of curiosity here, can you list for me all the fractions that are between 0 and 1? I don't think so, right? There's 1/2, there's 1/4, there's 3/4, but if you start, there's 9/10 right here, right? That's going to be huge. In fact, it's an infinite set. You can't actually build an infinite set here. So that is going to be using set builder notation. Another part, how about if you just want all the numbers that are greater than 3? So you want all the stuff that goes like this. Well, obviously you're not going to start listing all of them. It'll then take you forever. And then that's not including all the fractions inside here, all the square roots inside here past 3. So what we do, we just write X such that X is greater than 3, and there it is. There's our set builder notation. Now let's go back to this one here. How do you write this one, set builder notation? Ooh, that's a tough one here. Settable X such that, and then what would be the condition? What would be the condition so that you get all the fractions between 0 and 1? So think on that. Sometimes they'll throw out these little trivia questions for you, just to say, hey, do you know it? What condition would you make? And this is a trivia question here, so think about it during the weekend. So Mr. H, talk about it amongst your friends if you're totally bored out of your mind, and say, hey, what would be the condition so for me to have a rule that gives me all the possible fraction combinations of all the fractions that could be between 0 and 1. Okay, let's go on. I'll let you ponder that one. Okay. With that, we also have something called sets, and if two sets can come together, they come together in two different ways. Something called union. And what union means, you want the stuff that's in either A or B. You want all the stuff all gathered together as one little set. And it kind of shows you like this here. I want all the tan area, I want all the blue area, I want all the green area, everything. Okay, and it's designated by this little symbol called union, and U for union. Okay, sometimes there's also this called intersection. I want just the intersection. I want to know where the two meet together. And the notation for it is like this. It's the upside down U, but it really means intersection. It's kind of like the N part of intersection. All right, and then you go, okay, you just want all the stuff only where the two sets meet, only the stuff in the middle. That's what you want. Okay, so let's go for it here. Again, I'm going to go a little faster here because of time constraints here. So practice problem number 3. Can you give me the intersection? Then can you give me the union of A and B? Again, let you try it yourself first. All right, let me try it as well here. So intersection. What do the two sets have in common as you look at them? And as I look at them myself, it looks like 0. 0 is the only element that they have in common. 0 there, and nothing else. Okay, and union just means let's put everything together. The union or any kind of set really doesn't have to be in order. You can write the numbers any which way you like, but normally what we do is we write them from smallest to biggest, because then it keeps a little order in it as well. Okay, so with that, you can write individual numbers, or what you can do is you can also write an interval. And I think you guys know this about intervals. Interval can start somewhere, stop somewhere. And I think in high school, I think you guys looked at open dots and closed dots. Well, this is kind of like an open dot. Parentheses are open dots. Brackets are closed dots. And here's the different forms. There's interval, there's a graphing of it. This right here is called interval notation. This is how we say it. And this is, hey, look at that, set builder notation. So if you say, I want all the numbers between A and B, you say, I want all the x's such that A is less than x and x is less than B. Cool. That's called an open interval. A closed interval means you're including the A and the B together as well. So closed interval, so bracket A to B bracket means I want all the x's such that A is less than or equal to x and x is less than or equal to B. So you're including the A and the B into it. Okay, there's a whole bunch of other ones as well. Let me jump to this one. There's the first one we just covered there. There's the second one we covered, but you can go all the different ways here. You can not include the A but only the B. You can include just the A but not the B. You can start with A, go on forever to the right, but not include the A. You can start off with the A including the A and going off to the right again. Not including the B going off to the left, including the B going off to the left, and then you can have the whole entire real number line. So notice you have interval notation, set notation, and then you have the graph of it. Alright, just like to mention real quickly here on these ones right here, notice if you are next to the infinity symbol, those always have a parenthesis next to them, because technically you can't get to the smallest number in the world and you can't ever get to the largest number in the world. So what we do is we put a little parenthesis saying that it just keeps on going and going. Okay, so for you guys, can you please find, again we're going to include this union intersection stuff, can you find for me the union of interval 1 and interval 2, then can you find the intersection of interval 1 and interval 2? And give you guys a little bit of time, try it yourself. I'll pause the recording here. Alright, let's go for it here. And the way I like to do this here, I like to make a little graph. That's eventually I think you will not make a graph, but if you need to, make a graph initially. So if I say interval 1 is from -infinity to 5, there's my interval 1. So parenthesis at 5 going off to the left. Interval 2 is from -2 including -2 off to the right. There's my interval 2. And so that means I want the union. Union is all of it all together. So if you think about this as like a little sandwich, what we do is we're going to crunch these guys together onto one big giant graph. And if we do that, that's going to be from -infinity to +infinity. Notice there's a graph everywhere. There's at least one graph everywhere. Here there's actually both graphs, but there's at least one graph everywhere. So I like to sort of think about this as just crunching the two graphs on top of each other and just seeing what graph you have. Intersection means where do you have both graphs at the same time? What numbers fulfill both graphs at the same time? And again, if you crunch these together, if you think of these as wires, that's what I sort of think about them as wires, is where you have the overlap, where they're going to hit each other. And so the wires hit each other starting at -2, going up to 5, not including the 5. So a bracket -2, comma 5, parenthesis. Okay, that's one thing to cover. The other thing to cover in this section is the whole concept of absolute value. So just real quick, absolute value we say is a number that is always non-negative. So it could be 0 or positive, but it can't be a negative. So the proper definition of absolute value is really the distance from 0 to that number. So if we say the absolute value of 5, the absolute value of 5 is the distance from 0 to 5, which is 5. The absolute value of -3 is 3 because the distance from 0 to -3 is 3. So, and then the absolute value of 0 is actually 0, of course. So notice there's never a time where absolute value could be a negative number. So we say absolute value is a non-negative number. Okay, the algebra definition. Algebra definition says this. The absolute value of A is equal to A if A is 0 or positive, and the absolute value is equal to the opposite of A if A is negative. So there's my sort of the algebra definition of it. Again, I think you guys know this already pretty easy, so I'm going to let you guys do these 3 problems real quick here. I'll pause the recording and let you guys try it yourself. Alright, so let's go for it here. So absolute value of -10, 10, easy. This one you got to do a little bit of work here. So 3 minus 4 will be a -1, but inside the absolute value still. So then the absolute value of -1 is a 1. And this one here, got to do a little bit of work, some multiplication here. 2 times -3 is -6, and -6 plus 7 makes a positive 1. Absolute value of positive 1 is just still a 1. Alright, in the textbook also, I kind of like these here, they give you these little warning symbols. So as you look at this warning symbol, this is usually students get something wrong, or it's a problem area for students. So it tells you sometimes like, hey, the absolute value of a number actually can still have a negative value at the end. And so the way we make a negative value of something, we put a little negative in front of the absolute value. So if you want the absolute value of 5.3, but you want the negative of it, we just stick a little negative in front of the absolute value. It's the same thing here. Negative of the absolute value of -4. Well, this part becomes positive, but since the negative is hanging out in front, there's your little negative. And a decimal that repeats itself, absolute value of that is going to be that, but then you get the negative in front. So yes, you can have, after some computation with absolute values, you can still make it a negative by putting the negative out in front. Okay, the other thing that we've got to think about is something called the distance formula of a number line. And so if A and B are coordinates of a number line, I want to know the distance between the two. And the way we make distance between the two is we use absolute value. And if you use absolute value, then it doesn't matter which direction you choose. You can say A to B, or you can say B to A. It doesn't matter. So this is just on the number line. We'll get a distance formula for the coordinate plane later on. And so your example or your practice problem here, all yours. Find the distance from or between -7 and 2. Alright, so if we look at this here, I'm going to draw a little number line just to see where we're at here. So I got -7 and 2 over here, 0 is over here about. And so what we really are going to do is we're going to compute it based upon a little formula that says -7 minus 2. That makes a -9, and the absolute value of -9 is 9. So the distance from here to here has to be 9. Alright, also it doesn't really matter which one you use, the 2 or the 7, because you can also do this here. What's the distance from 2 to -7? Right? So distance between 2 and -7. And if that's the case, what's going to happen is subtracting negative, same thing as addition. And then you're going to get yourself a +9, and voila. It doesn't really matter which point you choose. You're just going to get the same answer anyways. And the distance from -7 to 2, or from 2 to -7 is 9. Okay, don't have time to cover this. Most of this you probably have covered in algebra. It is all the different properties with absolute value. Again, property and example. This is pretty important stuff. When you get to algebra, we really don't, when you get to calculus, we really just don't have time to cover it here. But absolute value of A is either going to be 0 or positive. If you have a negative number and a positive number, if you take the absolute value of them, it's going to be the same. If you multiply numbers, you can multiply numbers inside the absolute value or outside of it, so it's not going to matter eventually because you're still going to get the same positive number. If you have a fraction, you can split absolute values into the top and bottom. That's important in calculus. It does come up right there. Number 5 also comes up in calculus. That doesn't matter. We just tried that off the last problem here. It doesn't matter which way you go subtracting the difference between, or finding the difference between two numbers, you're going to get the same number. This one comes up in calculus. You're comparing the number itself to the absolute value of that number. And so true. The number is always going to be less than or equal to the absolute value of that number. Okay, and then this is the triangle inequality. Again, important. It does come up in calculus. If you're taking the absolute value of two numbers that are being added together, that is always going to be less than or equal to the sum of each of the absolute values of them. So I would say things that you're going to see in calculus, 4, 5, 6, 7, but these are just basic. 1, 2, 3 are really basic information you should know already from algebra. Anyways, don't have time to cover it completely, but I want you guys at least to see it. Okay, now order of operations. Let's cover that really quick here. We're just going to do a few problems here and go on. I think you guys know this. Please excuse my dear Aunt Sally. I write it like this because whenever you see multiplication and division, you're going to have to do that at the same time. You don't just do multiplication first and then division. You do them first whenever you look from left to right, whichever comes up first. Addition, subtraction, same way. When you see addition or subtraction, you're going to do it at the same time as you scroll from left to right along the number line. So I'm again going to give you guys just 4 problems real quickly here. Let you guys try them yourself. And I'm going to pause the recording for you guys to try it. Alright, let's go for it here. So use order operation to evaluate each of the functions here. So hopefully you got a negative 15 plus 20, which eventually made 5. On this one, notice division is coming before multiplication. So again, this whole concept of you got to do this first. So 12 divided by 6 would be 2. And then you got to do multiplication. 2 times 2 is 4. And then 5 minus 4 is a 1. Okay, 2 more for you to practice. Alright, and then let's try this one here. Again, whenever you see quotients, you got to simplify the quotient first before you can do anything else. In this case, 8 divided by 4 is going to be eventually a 2, and then 2 subtract 35 would make a negative 33. On the other side, anything in parentheses has to be done as well. So how about 6 minus 4 is a 2. Got to square the 2, makes a 4. And then eventually you get yourself a 1. Okay, then let's go through a few things here. Again, these are just summaries, something you should know from algebra. Some of them definitions here. Something called the closure property. Not going to really see it too much in calculus here, but it's part of the whole concept of real numbers here. We don't really talk about closure property in algebra. Closure property just means if you're adding 2 real numbers together, there's still going to be a real number. If you multiply real numbers together, you're still going to have a real number. So the numbers don't change. You don't just automatically just jump into complex numbers all of a sudden out of nowhere. Commutative property means you can add or multiply them in any order. Associative property, again, you can start off in any order if you have 3 or more numbers. Identity, for addition, identity is 0. That means if you add 0, you still get the same thing. For multiplication, if you multiply by 1, you still get the same number. And again, inverse. For addition, how do you get back to 0? Is you add its opposite. For multiplication, how do you get back to the 1? Is you multiply by its reciprocal. And then this one here, the distributive property. I think everybody is aware of the distributive property here. Some more properties here. 0 times any number is going to be 0. And then if you have 2 numbers multiplying to 0, that means either the first number or the second number is going to be 0. The whole concept of subtraction. Subtracting is the same thing as adding its opposite. Division. Dividing is the same thing as multiplying its reciprocal. And then all these properties that have to do with algebra skills here. So review them if you need to. These are kind of interesting skills there to sort of see that. And then the shorthand, I think you guys seen this before in algebra. If you say x is plus or minus y, what you're really meaning are, you're meaning two different answers. You want the sum answer, and then you also want the subtraction answer. Okay, and then particularly properties with fractions here. So again, if you're adding or subtracting fractions, you do the operation just to the numerators. Again, multiplication of fractions here, reducing of fractions, adding with unlike denominators, subtracting with unlike denominators, dividing and multiplying with unlike denominators, and something called cross multiplication, right? Whenever you see two fractions equal to each other, you can cross multiply by multiplying the denominator of one times the numerator of the other. Anyways, a whole bunch of different properties here. I think some of those have been already second nature to you. You already know those properties pretty well. So, let you guys try it yourself. Can you real quick do these operations here? We'll check our answer just to get the feel of working with fractions here, because that tends to be a little bit of a tricky part for some. Alright, let's go for it here. So again, whenever you are adding, subtracting fractions, you do need common denominators. Hopefully you've done it already here. So 7/4 now turns into 14/8, and added together gives you 17/8. The question always comes up, Mr. H, do I need to put this into a mixed number? No. I'm going to say this, if you want to, you can. But usually in pre-calculus and calculus, we actually want to keep them as improper fractions because they're a lot easier to work with. Whenever you do a lot of geometry stuff, geometry tends to want mixed numbers in there. Okay, this one. Okay, kind of funny little stuff here. In people that are mathematicians, people that do math for a living, have actually done original work in mathematics. Kind of funny, they divided to two groups based upon really this. In math, there's a little joke here that either some people are like algebra and hate geometry, and some people enjoy geometry and hate algebra. There's two kinds of mathematicians. And so the mathematicians that actually love algebra, what they do, they would keep it as 17/8. The mathematicians that love geometry and the whole concept of looking at figures and trying to figure out topology and all that good stuff here, they are the mathematicians that tend to write this as a mixed number. And so, kind of funny how even mathematicians, people that study math for their life, actually still favor one or the other. And I think in even in this classroom, right, or this, raise your hand if you like geometry. Like, wow, I like geometry. I like geometry. I like the calculating stuff. I like the looking at different figures. Okay, cool. And then you have these people that, raise your hand if you liked algebra. You didn't care for geometry, like whatever, but whoa, I like the logic of algebra. I like the fact that it makes sense. I like the fact that there's rules there that you... Okay, see, same thing happens. Same thing happens in math land with mathematicians. Okay, anyways, let's go for it here. This one, hopefully got a denominator of 15, and hopefully you eventually came up with 34/15. Okay, some more for you. All yours, go for it. Alright, and here what we do whenever we multiply fractions, remember what we do is want to cancel as much as possible. So 9 and 3 reduce, 7 and 14 reduce, eventually you get 3 halves. If you don't reduce, you can reduce later. Eventually when you get to this, you ask yourself, can I reduce this any more? And once you can't, then you're done. Dividing fractions, what we do is we change that up into multiplication, that's all. So 5/8 times 16/15. And then we do the same thing here. We reduce as much as possible, and eventually we get ourselves 2/3. Alright, again, this little warning idea here. There's some incorrect procedures that sort of is a habit for some students, or sometimes it doesn't clarify, and here's the correct answer. So take a look at those in the textbook. Those are pretty good just to clarify your thinking on a few things here. Okay, so let's add in the variable now. So let me jump to this here. And can you do this for me here? Evaluate the following expressions for the given values of the variables. So given that expression, if x is equal to 3, can you plug it in and simplify? All right, plug in the 3 for the x everywhere. That looks like that. You got to do parentheses first. So 3 subtract 2 first gives you a 1. Looking at any multiplication or division, yeah, you get 1 divided by 3. So we can actually change it into a fraction. That's no problem. That becomes 1/3 plus 3. And then we have to get common denominators, right? Actually, there's 2 different ways to do it. Let's do both, see which way you did it. For some students, what they do is they convert this into common denominators. Since they see 1/3 and 3, 3 changes into 9/3, eventually you get 10/3. Others of you probably did this here. You see a fraction and you see a whole number, and if you're adding them together, all you get is you get the mixed number. There's the whole number piece, there's the fraction piece, and actually it makes that number. All right, and let's do the last one here because of time constraints here. All yours here. Can you plug in the x, plug in the y, and simplify as much as you can? All right, hopefully you did that already here. So plugging in a -1 for x, plugging in a 3 for the y. Got to take the absolute value of 3. That'll simplify first. And then also, since you're subtracting a negative, you can just use that as a addition. And we just learned from the last one, if you have a whole number, if you have a fraction, you can write it as right there. And again, if you like geometry a lot, you're probably going to keep it like this. If you like algebra a lot, you're probably going to convert it into 22/3. And you can already guess what the author in the textbook is. Does he like geometry? Does he like algebra? And you'll find out that most of the answers in the back of the book actually have improper fractions next to them, so you know that he actually enjoys algebra more than geometry. Okay, with that we're going to stop. We don't have time to do the chirping of the crickets, but that's okay. We'll get into enough application questions during the course.